the third day of our first virtual ultra quantum matter meeting. So I just wanted to give the same reminders about questions before we get started. So if you're a panelist, you can go ahead and just type into the chat that you have a question, and then I can call on the speaker. Attendees can type your questions into the Q&A, and then I'll try to read as many of those as we can in the question and answer session at the end of each talk. Okay, with that, let's go ahead and get started. So the first talk today is going to be given by Chen at Caltech, and she'll be speaking about Fracton and Chern-Simons theory.
Thank you, Mike. And I'd like to thank the organizer for putting together such a virtual event under a very special circumstance to allow us to get together. So today I'll be talking about Fracton and Chern-Simons theory. So this is something I've been thinking about for almost a year now. And along the way, I talked to a lot of people and I got a lot of useful feedback. And you can see that there's a range of people that helped me with this project. So Xiuqi is my student, and Wilbur's my student, and also Meng and Michael and Zhang and many other people who are not actually listed, but maybe I probably have run into you in the past year and asked you about this question. And eventually, I think we have, well, I have settled something for myself, and I think this is now a legitimate direction to pursue. We're still at a very early stage of understanding what we're getting into, but hopefully this might be a new platform for us to think about fractons. Okay, so just get right into it. Okay, all right. So first I want to say that there's already another paper with very similar title called Fractonic Chern-Simons and BF Theories by Yizhi and Trisep and Sondi and Fiona. So it's similar, but it's also different, and I want to, and their focus is more on higher rank gauge theory, although I am more simple-minded, and the thing I'm going to talk about today are not higher rank gauge theories, it's simple gauge theories with Chern-Simons. It's the usual vector gauge theories with Chern-Simons terms, but we're trying to interpret what kind of fracton physics they can represent. Okay, yeah, so this is the usual Lagrangian for the 2+1 dimensional Chern-Simons theory. We have a vector gauge fields, the A's, and we can have a Maxwell term. The first term is the Maxwell term, and then the second term is the Chern-Simons term, the ADA term, and we can allow multiple components of those gauge fields, the AI, the big I, and big J. They label the different components of the vector gauge field. And the Chern-Simons term has a coefficient of Kij, where this Kij is known to be characterized by a symmetric integer matrix. So every entry is an integer and it has to be symmetric. Okay, so this is well known, and this has been studied very extensively. And in particular, we know that, for example, if case just the number 1, it represents the integer quantum Hall system. If case 3, it represents the fractional quantum Hall system. And if case like a matrix, a 2x2 matrix of 0, 2, 2, 0, this represent a simple Z2 gauge theory, or what we call toric code. So this is very well known in 2+1 dimension. And if we want to study fracton, which has mostly been a phenomenon that we discuss in 3+1 dimension or even higher, we want to take the dimension to be 3+1. And in order to increase the dimension, instead of making the vector field, instead of making the gauge field to have more components, what we do is instead to take the labels, the components of the gauge field to take value in an infinite range. So here in particular, this big I and big J, we'll take them to be all kinds of integers, all integers. And I will soon explain why we want to do this. So let me emphasize that here, the mu and nu and lambda, these are still 2 plus 1D. So it takes value in 0, 1, and 2, but not 3. And at the same time, we make these capital letters, this big I and big J, to take value in all integers. Okay. So correspondingly, this K matrix now become infinite dimensional. It's still a matrix, but it extends indefinitely, and it has integer entries. And the simplest case that we can try to think about is the case where K is purely diagonal. So it's infinite dimensional, but the only non-trivial entry is on the diagonal. And let's say it's 3. Okay. And physically, it's easy to interpret what that is saying. That is saying that we have a bunch of 2-dimensional layers. Each layer is a nu equal 1/3 fractional quantum Hall system, and we just stack them up along the z direction. And of course, each layer will be labeled by this big I or big J, and very simple. And the reason we want to think about this kind of situation is, of course, this is already representing some kind of fractal physics, even though it's very trivially a 3-dimensional fractal. But it is a fractal because, first of all, the ground state degeneracy of this system, if we think of it as a 3-dimensional system, then the ground state degeneracy is 3 to some power, where the power is the number of layers, of course, in the z direction, because each layer has a ground state degeneracy of 3. If you put it on a if you put it on a torus. And so the ground state degeneracy increase exponentially with the height in z. That is one crucial property of a fracton. And secondly, the point excitations, the quasi-particles, they're fractional, and they move in each individual plane. Let's say these layers are not coupled, and because everything's gapped, so the coupling, even if it exists, is non-relevant. So in a simpler situation, we can just imagine that all the layers are decoupled, and the fractional quasi-particles move in each layer only, and they're planons in the fractal language, meaning that their point excitation moving in a 2-dimensional submanifold, even though this model is 3-dimensional. And of course, this is because it's a pure stack of 2-dimensional things. And that's another feature of fractal, that is the existence of point excitation, which doesn't move in all 3 dimensions. Okay. And another one is the entanglement feature, where you take the thing I draw here is a cylinder. If you take a cylinder and calculate the entanglement entropy of the cylinder, you will see that there's an area law term, but after the area law term, there's a subleading term that's linear in the height of the cylinder, just because each layer that intersect the cylinder will contribute a constant topological entanglement entropy. And if you add them up, that will give you a linear term in the entanglement entropy for the cylinder. Okay. So these are all the hallmarks of what we call fractal physics. Although originally, when fractal models capture people's interest, they show up in much more non-trivial models than this. But this pure stack of 2-dimensional fractional quantum Hall is some kind of fractal. And we want to think about it as a trivial kind of fractal. But this is too trivial. So the question is then, can we get anything more non-trivial from this formalism, and in particular from this formalism of infinite components of vector gauge fields, and then we use the Chen term to describe. We try to use the Chen term to describe something that can emerge in 3 plus 1D. Okay, so we can make things slightly more interesting by taking not just a purely diagonal matrix, but a tri-diagonal matrix where the diagonal is all 3, and the next diagonal is all 1. And you can see that I've made the matrix have periodic boundary condition, and I'm going to call this matrix K 131. So this is a legitimate a symmetric integer matrix, and then we take it to be infinite dimensional. So we take the dimension this n to be bigger and bigger to infinity. So this matrix has been this Chen theory with infinite component has been studied back to the 90s and 2000. Maybe there are other papers on this subject where people think about a system where it started from a stack of fractional quantum Hall with nu equal 1/5. And that will be described by a K matrix, which is diagonal, with the diagonal being 5. But then if we consider interactions between the layers, for example, if we consider Coulomb repulsion between the layers, then the electrons between the neighboring layers will try to repulse each other. And that leads to the decrease of the diagonal from 5 to 3. And then the next diagonal becomes 1. So people propose this as a possible phase for this coupled three-dimensional fractional quantum Hall system. And a range of weird property showed up, and this is already discussed in this paper. For example, in the limit of system size, the height of the system going to infinity, the statistics, or in fractional quantum Hall language, and the charge in each layer that's being accumulated due to the flux in some other layer follows a very peculiar formula. Here, theta ij is the statistics between the flux in each layer, and that's because each flux accumulates some charge across all the layers. And you can see that it's exponential in the separation of the layers, and then but it's exponential of some irrational number. So there's some irrational statistics and irrational charge showing up in this system. Of course, the irrational number only shows up in the limit of infinite system size. If it's finite system size, everything remains rational.
Sorry, Xie. Is there any reason why they start with the nu equals 1/5 instead of 1/3?
Good question. If you go to 1/3, you get K111. I'll talk about this later, but K111 turns out to be a gapless. So this 131 is gapped.
Okay.
So let's stay with the gapped case first. The gapless case, yeah, let me not say too much. I might come back to that. I will come back to that much later in this talk. So, so we can calculate the ground state degeneracy, and it turns out to, well, Xiuxi did this, and it turns out to be a very complicated formula involving, again, irrational numbers. And you can see that in the limit where system size goes to infinity, it's 3 plus square root of 5 to the nth power. It approaches an exponential form, but never exactly. And if we consider the fusion group of planons of this charge attached to flux fractional excitation, this group has 2 generators, and each generator has very big order. So the ZFN is one part of the fusion group, has 1 generator, and the second one is Z5FN. So the order is 5 times as large as the first part. And that generates the whole fusion group. And Fn is some Fibonacci number. So exponentially growing, but very weird. Okay. So this is of course, at that time when people studied as a fractional quantum Hall system, they were not trying to interpret as Fracton because there was no Fracton at that time. But now we'd like to think about it in the Fracton framework. It is a kind of Fracton. This turns out to be a gap system, and there's some fractional excitations, and there's some ground state degeneracy that goes roughly exponentially, and there's a very huge fusion group for the planons, for the things that moves in the plane. So it is a kind of a Fracton model, although it's a very different kind of Fracton model than the ones we know. The one.
Jake,
Yeah.
can I ask a question? Can you give some intuition on where these irrational numbers come from?
Irrational numbers?
Yeah.
Right. So, so for finite system size, everything's rational. But if you take the limit, then it becomes irrational. I don't know whether I can answer this question in a meaningful way. For example, when you calculate the ground state degeneracy, the way Xiuxi did is to have some recursion relation. As you increase the system size, the ground state degeneracy of n and n minus n plus 1 give you a relation to n plus 2, and somehow this shows up. I don't know what other thing I can say. It's yeah, it's very weird. Okay.
Okay, thanks.
Yeah, sorry. So if we compare it to what we are used to, or the most popular model in Fracton, this X-cube model, we see very sharp contrast to what happens in X-cube. X-cube model is this stabilizer model on cubic lattice with this X meaning sigma X and Z meaning sigma Z. So the Hamiltonian will be a tensor product of a bunch of sigma X around the cube and a bunch of XZ.
Could you please go back to the previous slide?
Oh yeah, sure.
So what is this number, the 3 plus root 5 to the n, etc.? What is this number? This is the ground state degeneracy?
Yes, so if you look at the first line, it turns out to be an integer. This line is an integer, miraculously. But then I'm just saying that if you want to think about the thermodynamic limit, roughly, because the other terms are very, very small compared to the first term. So it's the first term that grows exponentially. So roughly it approaches this exponential form, but this is not.
But it is but the first term is an integer.
The first line is an integer.
It's not obvious to me, but
it's not obvious.
Yeah, no, it actually is obvious. Thank you.
Yeah, exactly. It's not obvious. Right. So if we compare to what happens in the X-cube model, for example, let's compare to what happens to the plane now. What happens in the X-cube model for the plane now, for the fractional excitation that moves in the XY plane. And that we know are generated by very simple operators. For example, one plane now is generated by a pair of sigma X string. So these a pair of the red lines, they generate one kind of plane now. The other one is a string of sigma Z on the dual lattice, also moving in the XY plane, but only in a single plane. So each of these planons, they have order 2. They don't have exponentially growing orders. If you fuse 2 of them, it becomes identity, obviously. And it's the number of generator that grows linearly. The number of generator grows linearly, and that gives you a huge fusion group that is representative of Fracton physics. And then the statistics are very simple because everything's sigma X, sigma Z. So all you can have is a pi statistics, and it only comes from the X and Z type of planon that touch each other, right? So it doesn't go very far. It doesn't go across the whole system. It only goes to the nearest neighbor, and that's it, and then it stops. If you calculate the ground state degeneracy goes roughly as 2 to the 2n, yeah, 4 to the power of n, because and it's not like irrational number to the nth power or something. And more importantly, what we understood about this X-cube model is that it has a foliation structure that if you want to grow the system size in the z direction by, say, 1, what you can do is to just add a decoupled layer of 2-dimensional toric code or 2-dimensional Z2 gauge theory, and then do some smooth deformation or local unitary transformation, and then map from one side to the other and increase the system size in that way by doing this. But this from this we'll see already why it doesn't, the K131 model is very peculiar, because if we can do this foliation structure, then the ground state degeneracy would grow simply by a factor of 2 every time it increased by 1, right? So it would be 4 to the nth power in the large system size limit. Or just every time it grows by 1 in the z direction, it grows by a factor of 4. And so it has a very simple exact exponential scaling of ground state degeneracy. And all the planons just come from the layers you add, just comes from the torical layers. So the planons all have finite order. The order won't be some irrational number. And then the statistics also come from the planes, the ENM particle in the toric code. So it will be very short range. There won't be an exponentially, it won't go very far, not even exponentially decaying tails or polynomially decaying tails. There's no tail, it's just short statistics. And then beyond certain range, it becomes 0. And because of all this, we can see this K131 model is not foliated. It represents something that we have not seen yet in fractal physics. It is simpler in some sense than some other models we have been discussing. For example, the XQ model, even because it doesn't have a fractal, meaning that point excitations which get stuck in space, which doesn't move on itself. So all the fractional excitations in this formulation of K-matrix, because it comes from the 2+1D formalism, every fractional excitation is a planon, so it moves in a plane. But otherwise, it's not foliated, while a lot of the other models we see, at least the stabilizer models and many others, are foliated. Okay. On the other hand, this K-matrix formalism, we know that it can allow us to study foliated fractal physics as well. And this is an example that Wilbur and Kevin and me wrote up last year. So this is a K-matrix, infinite dimensional. And you can see that it's translation, well, it has a period of 3, and then a translation invariant. And then it's also close to diagonal. So diagonal, next diagonal, and next diagonal. Okay. And the way to interpret what this K-matrix represents is by taking the inverse. And once you take the inverse, you see that if we ignore the ones, then it's a bunch of decoupled Z2 gauge theories. If we get rid of the ones, it's a bunch of decoupled Z2 gauge theories. But now we have the ones. It means that the Z2 gauge theories, their fluxes are they're coupled in some way. They have mutual statistics. So that tells us that there are a bunch of planons in this model. We label them by this ENM, but this ENM will have some statistics among them. In particular, this M's will have statistics between nearest neighbors. And if you compare this to what happens in this 131 case, you see a very sharp contrast. And in particular, this foliated K-matrix, the K-matrix is close to diagonal, or in a sense, local. We would say local. The K-inverse is also local. It's also close to diagonal. But on the other hand, the K131 matrix, the K-matrix is very local, but the inverse is everywhere. So this is an inverse that I took for a 7x7 matrix, and you can see their number populated everywhere. And if I take a bigger one, it's still populated everywhere. But the entries are decaying exponentially. So that's true. So in this case, the entries decay exponentially according to the distance from the diagonal. So it's not that non-local, but still very weirdly non-local. Weirdly not exactly local. So for this foliated K-matrix, what we could do is to study the foliation structure using the K-matrix formalism. And in particular, what we did is to find a W matrix. So this W matrix, it looks very big, but actually it's a local one because all the non-trivial action is within this blue dash box. So only within this blue dash box are there something non-trivial. Outside of this blue dash box, everything's just diagonal 1. So the only non-trivial action is within this 7x7, or I don't know how big, block. And then we can apply that to an infinite dimensional K-matrix. And what turns out to happen is that we can decouple a block here, within this red dash box. We can decouple this block out of the original K-matrix. And then if we remove this block, if we remove that, the red box, then everything goes back to the original form of the K-matrix. So the rest of the system takes exactly the same form as the original one. So this is exactly what we have been showing using pictures, but now we're doing it using the K-matrix formalism, where we have to start from a slightly bigger system, do some smooth deformation. Here, the smooth deformation is by redefining the gauge fields in terms of this W matrix. And what we decouple here, if you look at this 4x4 block, what we decouple is some Z2 cross Z2 twisted gauge theory in this case. And then the system size shrink by 1. Okay, and of course, the point of this paper was that this model turned out to be a twisted, what we call a twisted foliated model, that is different from the X-cube model in a very interesting way. But that's not the focus of my talk today. Okay, so as I've shown you that using this infinite dimensional K-matrix, we can potentially capture some very interesting fractal physics. And the reason we're trying to do this is because we want to go beyond exactly solid models. A lot of the things we have been doing for gap fractons is based on exactly solid models, but exactly solid models are getting harder and harder to deal with. We can do so much, and then we're too frustrated. So I was hoping to get a simpler formalism which allow us to deal with things in an easier way. For example, when we do this, we used to this foliation process using local unitary transformation. That's too hard. Now we just need to deal with matrices, infinite dimensional matrices. But a bonus of this is that we actually turned out to find, oh, sorry. I want to say that first for the foliated models, we hope to find new examples and calculate their properties and study their equivalence, study the equivalence between these models using the K-matrix formulation. Hopefully that would be easier to do than exactly solvable local unitary transformation. Excuse me. And then as a bonus, we also found non-foliated models, things that we didn't expect to see in exactly solid model. And if you think back, these kind of K131 kind of physics, this irrational kind of physics, they cannot possibly show up in an exactly solid model. So it's kind of like the chiral physics that we miss in 2 dimension if we stick with exactly solid models. So now with the K-matrix, we can talk about them, we can calculate their properties. And of course, the key question is how to, now without this foliation structure, how should we think about it? How should we think about their, for example, the renormalization group transformation for these models? That I don't know yet, but it's an open question. Am I out of time already?
No, you have, let's see. Sorry, no, you still even have 3 minutes until the question period, but it's okay to go into the question period a bit.
Great. But first, we want to be sure that we're doing something legitimate. That's something I've been bothering me for the past year or half a year, which is, are these things real? To what extent should we trust this formulation just by simply taking the components to be infinity? Are we really describing 3-dimensional physics? For example, we want to know whether they do represent local 3-dimensional local models, or is locality there? And this question pops up because this K131 example and some other examples, they look so weird. There are these very long range statistics, which bothered me, which made me feel that there might be something wrong with this. So I want to be more sure about whether we can write down a lattice model realization for these.
Why is that a problem? I mean, so every layer, if we know every layer, the K-matrix, the Chen theory in every layer represent a local theory in the layer, and we just have like a short-range coupling between the layers, meaning that the off-diagonal component of the K-matrix is just a local. So wouldn't that imply it's a local 3D system?
Yeah, but the off diagonal, the Chen-Simon term is not really describing interaction. It is.
Well, it describes interaction between charge and flux between different layers. Is that right?
Oh, right, yeah. So let me say this first. Yes, great point. So in terms of, so originally this was not a problem for the 131, of course, because everything was done in terms of Laughlin wave function. You can write down Laughlin wave function, you can write down some pseudo potential, and you can calculate the energetics, that's fine. And I'm comfortable with that. But once we try to go a little bit further, for example, with K-matrix with negative entries, or something that with 0 or somewhere, then things I don't know. I just I don't know how to interpret that. So and I want to be able to do things more generally, not just stick with one example. I want to talk about, for example, what class of K-matrix we should be thinking about, and what kind of physics they represent, things like that. And in particular, I want to know about the form of the string operator, because that is very important if I try to think about the fractional excitations and how to do RG, for example, for these systems. And in the Laughlin wave function formalism, it's not very obvious to me. For example, when in this 131 example, there are planons that have non-trivial statistics, even though they're separated very far away. Then the question naturally is, the string, usually we think about string operator creating an excitation here. But now if they have non-trivial statistics, even if they're separated in the z direction, meaning that the string operator is more like a membrane operator, right? And I want to know that, is there any locality related to the string operator in the z direction? Or should we really think about it as a membrane operator, that the excitation is actually a loop excitation? So that was bothering me. And if you look at the statistics of the 131, it is exponential in the separation between I and j, and the base is smaller than 1. So that's good, meaning that it's exponentially decaying statistics. But exponentially decaying statistics is not exponentially decaying interaction. It's saying that there's statistics. So I was not comfortable anyway. So I wanted to get something more concrete that I can, or maybe just because I'm more comfortable with lattice model. Okay. So what we were able to do is to say, okay, we're able to write down a lattice realization for quasi-diagonal K-matrix, meaning that K-matrix with entries that's close to the diagonal. And K-matrix are integers, so there's no issue of decaying tails. It's just cut off at some point, and then everything else further is 0. So for quasi-diagonal K-matrix, we can find a lattice realization, and we can write down the string operator. And so the model is not exactly solvable, so we cannot prove rigorously these things, but we're pretty comfortable. We're pretty confident that this is the kind of physics underlying the K-matrix. And then we can talk about whether the model is gapped or gapless. That turns out to be just a field theory calculation. So the lattice realization is given by very simply a stack of integer quantum Hall. So we take a bunch of integer quantum Hall, and then we assume that they have planar U1 charge conservation symmetries. But the charge conservation symmetry comes in a bunch of varieties. There's A1 and A2 and A3, and you see that they might overlap. So the first 3 layers carry charge under A1, and the layer 3, 4, 5 carry charge under A2, and so on and so forth. And then what we do is to gauge the U1 symmetries, make them dynamical gauge field and gauge it. And then we get a Lagrangian term that looks like this, where the first term describes a bunch of very simply integer quantum Hall. And the second term describes the coupling of the charge in each layer to the external gauge field, and according to, of course, how much charge they carry under each of the global U1 symmetry. And then we integrate out the fermions, we'll be left with the K matrix that we want between the big A's. Okay, so so if we write down the Hamiltonian for this lattice model, there will be a bunch of fermion hopping, and of course attached to the gauge field. And then there will be electric field term, there will be magnetic field term, and then there will be, we also put a gauge symmetry as a term in the Hamiltonian, where the gauge symmetry is enforcing that the divergence of the electric field is equal to the charge, and so on and so forth. Okay, and what we learned, one thing very important that we learned from this exercise is what the string operator looks like. Oh, sorry, I forgot to mention that this particular prescription, where we have 1, 2, 3 coupled to A1 and 3, 4, 5 coupled to A2. This one exactly gives us the 1, 3, 1 K matrix. And you can change the assignment of charge to get some other K matrix, but this formalism applies to all quasi-diagonal K matrix. Okay, so if we want to write down the string operator, what we can do this in terms of the lattice degree of freedom, and the lattice degree of freedom are the fermions and the lattice gauge fields, which I draw with green, and the fermions are black. Okay. And in terms of Chen-Simons gauge field, the string operator is very simple. It's too simple. It's like e to the I and the integration of the gauge field. But this is too simple because it doesn't show the extent in the z direction. It looks like it's just one component of the A field, and it gives you the feeling that they don't touch each other if they're separated in the z direction, but of course that's not true because the Chen-Simons gauge fields are not really local degrees of freedom. So secretively, they actually do touch each other, and now we can see that from the lattice degree of freedom. And what happens is that, let's say we want to write a string operator for the charge vector of 1, 0, 0, 0, 0, meaning that we want to insert a 1 gauge charge for the first dynamical gauge field. What we can do is to, in terms of lattice degree of freedom, we write this string of e to the IA, which create 1 gauge charge for that particular dynamical gauge field. And then this is Chen-Simons, so gauge charge is attached to gauge flux. So we have gauge flux term, but the gauge flux term, the coefficient, it can be across multiple layers, and it comes according to the K inverse matrix. The K inverse tells you how much fractional gauge flux is attached to a particular gauge charge. And then on top of that, the matter field has to respond. The matter field has to evolve adiabatically according to how much gauge flux we inserted for the gauge field and how they couple to these gauge flux. And there's an adiabatic evolution, but those are just on top of the matter field. And all together, they make up this string operator. And from here, we learn that the string operator goes as the fractional part of the K matrix. And in particular, for the 1, 3, 1 case, the fractional part of the K matrix, the K inverse matrix, decays exponentially. So we're safe to say that the string operator is local in the z direction, that the excitation is still a point excitation, not a loop excitation. And even though it has an exponential tail, it's an exponentially decaying tail. It's not too extended.
Just sorry, we have just about a couple minutes left
yes.
until the end of the talk.
So let me just very quickly go to the end. Let me just mention one more point, that this gap versus gapless. The spectrum you can calculate just using standard field theory calculation. And it turns out that, for example, this 1, 3, 1 is gapped, but 1, 2, 1 or 1, 1, 1 are gapless. This is just very simple. It's the energy levels are associated with the eigenvalues of the K matrix. So if the K matrix are gapless, then it's gapless. And then for these gapless ones, I I really don't know what's going on. And there's a bunch of possibilities. It could be unstable, and there could be translation symmetry breaking, or it could be some, I don't know, gapless spin liquid, gapless fractal. There's not much I can say, although there's something interesting about these gapless cases as well. For example, in the 1-to-1 case, the K inverse matrix does not decay. The fractional part does not decay, meaning that there are some membrane operators, but I won't try to read too much into that. Okay, so that's it. Yes, I should leave some time for questions. So let me just put my, very quickly go through my open questions. Open questions, basically. A lot of things we don't know, whether given a quasi-diagonal K matrix, whether they're foliated, and how to think about their equivalence, and what does the gapless K matrix represent? But this now we're confident that this is something real, and then we can hopefully use a lot of math that we know about these infinite dimensional symmetric K matrix to study fractal physics. That's it.
Okay, thanks. So we're pretty much out. We're actually out of time, but nonetheless, I want to get to a lot of questions. I see there are actually quite a number of interesting questions in the Q&A, and I'm going to have to pick and choose. Nadia, I also see your question in the chat. I think maybe we'll be able to get to that. So here, these two questions kind of go together, so I'm going to read them both. I think they're closely related. So one is from Drew Potter, which says, so far, there's just a single integer index I, which takes integer values corresponding to a 1D stack of topological orders. To describe a 3D foliated model, maybe like the X cube, do we need to promote K-matrix indices to take values in Z cube to represent foliations in all three directions? And let me read, before you answer it, I just want to read a different question from Fiona Burnell, which is closely related. For rotationally invariant models like X cube, can we think of K-matrices associated with each direction? Should we? If so, how do I tell if a K-matrix represents a theory that is anisotropic?
Yeah, great question. And the last slide, did I get out of screen sharing?
Yeah, you're not sharing the screen anymore, but you could share it again.
So one thing I put on the last slide but didn't get time to mention is that the X cube model, actually, we can't do this. And the reason we can't do this is because it's three-foliated, if you know what I mean. But this K matrix is kind of just capturing one foliation. And I think these two questions are exactly on that point, that we only see planons. And that's what I want, because I want to start from things simpler and then build up. But for example, the X cube model, we have a proof that we cannot do it with quasi-diagonal K matrix. It just doesn't fit there. There's something wrong. But the something wrong is just because it's three-foliated. So my hope is that this K matrix formalism would allow us to understand better the one-foliated, or well, it's some things are not foliated. The 1-to-1 is not foliated, but the ones with planons first. And then to go from there to X cube is not too hard, I think. We have couple layer, we have a bunch of things. So maybe, but then of course, it will be a great thing to see if we can promote indices to like Z cube or some other things, and then capture three-foliated or things with Fracton even. That would be better. But for now, I think it's, I'm trying to deal with the planon case first.
Good, okay. I think we're running a little bit over time. So unfortunately, though, I see a lot of interesting questions.
And sorry, I'll try to address them in the chat.
Yeah, you can always respond in the chat, or you can probably also see the Q&A feature, and you can type in, you can see some of the questions there, and you might be able to type type in answers if you have a moment. Okay, so thanks again, Xie, for a very nice talk.